Lecture number 10, the regenerative Brayton cycle, and again we'll be doing some solve example. Example 9.7 and example 9.7 of Moran and Shapiro. Evaluating the thermal efficiency of a Brayton cycle with regeneration. A regenerator is incorporated in a cycle example 9.4, which we have already solved in lecture number 8, for which a video is also available. Determine the thermal efficiency for a regenerative cycle if the effectiveness is 80%. Plot the thermal efficiency versus regenerated effectiveness ranging from 0 to 80%. We will be not doing it, obviously. Yes, if we are doing some lecture on the engineering equation solver, then we will be doing this thing. A regenerative gas cycle operates with air as a working fluid. The compressor inlet state, the turbine inlet temperature, and the compressor pressure ratio are given. The regenerator have got the effectiveness of 80%. So solving this using the same data as was in example 9.4 and as it was actually in lecture number 8, with the same assumption, we would be having the enthalpy at the inlet of the compressor H1 as 300.19 kilojoule per kg. Enthalpy H2 was, which we have determined, was actually 579.9. Enthalpy H3 was 1515.4 and H4 was 808.5. That was actually from the previous example 9.4 lecture number 8. Then we have installed a regenerator which has got the effectiveness of 80%. So if we have got the regenerator, the regenerator would what actually would happen, like the heat which would be transferred from 4 to 1 actually, the heat which will be transferred from 4 to 1 actually, some of the heat would be incorporated in a regenerator, and there would be actually increase in the air temperature which would be inlet to the compressor, combustion chamber, which over here it is written as combustion chamber is at state number X, from X to 3. So what we are doing over here, the at number 4, when we are actually exiting the turbine, the heat is actually given to the regenerator, and the heat is transferred from 4 to Y, which is actually outlet condition, which is over here somewhere here, and then this heat would be actually gained by the regenerator and by the air which is passing to the regenerator from 2 to X, which is somewhere over here. So if it is a perfect regenerator, this heat transfer, which is actually from 4 to Y, would be actually transferred to the heat to the air which is actually leaving from 2 to X over here. But as it is actually said, like the regenerator has got the effectiveness of 80%. So that means like the temperature at state X over here would be actually less than the temperature which is supposed to be actually at somewhere here, which is actually some T4. That would be equal to T4 anyway. So this is actually the example of perfect regenerator and the imperfect or the regenerator with have got the less effectiveness. So let's say we have already found the other value at state 1, 2, 3, and 4. Let's find the value at state number X. So as the effectiveness is given, which is 80%, so effectiveness formula would be the Hx minus H2 divided by H4 minus H2. This is the imperfectness, and obviously this is the perfect, which is actually H4 minus H2 would be there. Using the formula, we can find the enthalpy, and that enthalpy would be equal to 709 to 762.8. So now what would be the efficiency? So the efficiency would be the same actually. The work done of the turbine from 3 to 4, minus the work done of the compressor from 1 to 2. But now the heat is not transferred from 2 to 3, but it is actually transferred from this point, which is X point, towards the 3 point. So we have actually reduced some of the heat, which is actually this one. So deducting this heat from the previous value, which would be now H3 minus Hx now. So the work of the turbine minus work of the compressor divided by the heat which is actually transferred in the combustion chamber. So the combustion chamber previous heat was actually 15.4, sorry, not the H3, minus that was actually minus H2, and which is somewhere H2 was 579.9. Now we have got the other value which is actually 762.8. So now the efficiency is gone up to 56.8%. Previously it was 45%. So that's obvious, like by installing a regenerator, the thermal efficiency of the Brayton cycle increases. Now moving towards the another example, um, example 9.8, but I'm using another book which is the thermodynamic and engineering approach by Yunus Angel and Bulk. Um, This is the example of the intercooling and reheating, intercooling in the compressor and reheating in the turbine. We are using the single stage intercooling and the single stage reheating in the turbine and single stage intercooling in the compressor. An ideal gas turbine cycle with a two-stage of a compression as a two-stage of expansion has an overall pressure ratio of 8. Air enter each stage of the compressor at 300 Kelvin and each stage of the turbine at 1300 Kelvin. Determine the backwork ratio and the thermal efficiency of the gas turbine cycle if we are assuming there is no regenerator and if we are assuming that there is an ideal regenerator with 100% effectiveness. Compare the result with those obtained in example 9.5, but definitely we have not used the example 9. Not done the example 9.5, but anyway we'll be comparing it. By perfect regenerator, again I've already said, like the perfect regenerator would be like the temperature at which it was T4. So this temperature would be equal to temperature which is exiting the regenerator, which is actually T, let's say Tx over here. So the same example would be here. It's a like we have got the intercooling. So air enter each of the compressor at 300 Kelvin. So that means like whatever state 1 is actually inlet of the first stage of the compressor. Stage 3 is actually inlet of the second stage of the compressor. So if it is perfect intercooling between 2 and 3, then the temperature at state number 1 and state number 3 would be equal, and also enthalpy at state number 1 would be equal to enthalpy at state number 3. Um, it's also say like the each of the turbine stage is actually at 1300 Kelvin. So that means like inlet of the first stage of the turbine is 1300 Kelvin, and the second stage then after reheating, so we are doing the reheating at 1300 Kelvin as well. So after reheating, the temperature at state number 8, which is actually inlet of the second stage of the turbine, is also 1300. So that also mean like enthalpy at T1, sorry, enthalpy at H6 would be equal to enthalpy H8. Also, if there is a perfect, as the compression ratio is same as it's like the ideal turbine with a two-stage compression, a two-stage expansion, and overall pressure ratio is the compression ratio is same. So that also mean like the temperature at exit of the compressor T2 would be equal to temperature T4 as well, and also with the enthalpy that would be equal to enthalpy at H2 would be equal to enthalpy at H4. Having said that, if we are doing the regenerator, so 9 to 10 if it is, so regenerator, sorry, I do not have got the schematic diagram, but regenerator would be actually from 9 to 10 over here if it is perfect regenerator, and the regenerator from the gas side, and from the air side the regenerator would be from 4 to 5. So if it is perfect regenerator as well, so the temperature at T4 would be also equal to temperature at T10, and same would be the enthalpy. And if it is perfect regenerator also, so T5 would be equal to T9 as well. Sorry, T5 would be equal to T9 as well, and also T7 as well. So this is the example which would be simplified if we are assuming all the ideal situation, as there is no irreversibility involved in it. there is perfect intercooling, there is actually reheating at the same temperature, and the regenerator is 100% efficient. So the question remains very easy now. So steady flow operating condition would exist, and then the standard assumption would be applicable, and we are doing the standard air condition as assumption. Kinetic and potential energy changes are negligible. Using the TS diagram, I've already discussed like P2 by P1 would be equal to, if it is perfect, if the compression is perfectly, so P2 by P1 will be equal to P4 by P3. And as the both of the compression ratio is 8, so that would be uh, for the each single stage, that would be 8 raised to power 1 by 2, and that is equal to 2.83. Similarly, for the turbine, P6 by P7 would be equal to P8 by P9. That is actually equal to 2.83 for the same for the turbine expansion as well. Already discussed, T1 would be equal to T3 as the inlet condition are same. So enthalpy H1 would be equal to enthalpy H3. Um, T6 would be equal to T8 inlet condition of the turbine. So enthalpy H6 would be equal to enthalpy H8. T2 would be equal to, after the compression, T2 would be equal to T4. So enthalpy H2 would be equal to H4. H7 would be equal to H9 as well. And as so enthalpy the same. Also for the regenerative, I've already said like we can actually find the enthalpy H5 from H7 as well and T7 as well. And in the regenerator TH10 can also be found at from the temperature T2 or T4. Now, using the table and the A table, which actually we have previously used in lecture number 8, uh, T1 is equal to 300 Kelvin. And so from table A17 in, that's what actually it's a like Unisenja. But if I'm using the Moran and Shapiro same table, that would be A22. Uh, so using the same table, we have already done it. So the enthalpy at 300 Kelvin would be equal to 300.19, and the pressure ratio is at state 1 would be equal to 1.386. And now compressing into the state number 2. State number 2 compression is 2 point, sorry, let me check it. So state compression is 2.83 multiplied by 1.386. So that would be compression ratio 2.83 multiplied by 1.386. We will be having the compression ratio of at state number 2 we'll be having PR2 at 3.92. Now let me check at 3.92. Let me find the temperature and the enthalpy. So 3.92 would be somewhere the pressure ratio 3.92. So yes, somewhere here. So 3.806 and 4.1 4.153. Also the temperature is at these two value would be equal to 400 and 410. So 3.92 our pressure ratio is, and the enthalpy is, so roughly it is somewhere between them two, like 400 and 410. So I'm assuming like 403 4 would be there, and obviously the same thing would be there like 400 and let's say yes 405 and something like this. So yes, doing the interpolation, I would say like you can find the enthalpy at a pressure ratio which is 3.92. So yes, at 3.92, the temperature is 403.3 as of interpolating, and the enthalpy is 404.31. So this would be the enthalpy at H4 as well, and this would be enthalpy at H3 as well. So moving towards the state number 6, which is inlet of the first stage of the compressor, sorry, first stage of the turbine. So the temperature is given, which is 1300 Kelvin. So let me find the enthalpy at and pressure ratio at 1300 Kelvin. So at 1300 Kelvin, which is somewhere here. So, at 1300 Kelvin, we have got the enthalpy, which is 1395, and we have got the pressure ratio, which is actually equal to 330.9. So moving to back to the question. So enthalpy was 1395.97, and actually pressure ratio is actually 330. Now using the same formula as we have discussed previously, so that would P7 by P7 by P6 would be equal to P7R by P76. As we have been given P6 by P7, so that was under root 8. So 1 over under root 8, or we can say like 1 by 2.83. So multiply by 330.9, we can find the PR7, which is 117.7. Now back to the A table using the pressure ratio of 117. Let me find the temperature and enthalpy. So yes, we have got the, again we do not have got the perfect pressure ratio 117. So our value is somewhere between 114 and 123. So assuming like again it is somewhere in the middle. So the temperature is 1000 and 1020. So I'm assuming like that would be somewhere 1010, and obviously the enthalpy is somewhere between them. So moving back to the question. So yes, so the temperature is somewhere around like 106.4. Let's say I was assuming like it would be somewhere in the middle, like, but less. Yes, you do interpolate, and the enthalpy is actually 153.33. Um, this enthalpy was actually found at temperature T7 over here. This is also enthalpy at temperature T9, and obviously this is again the enthalpy at temperature T5 as well, as these are the perfect reheating. Now, as we have already found the enthalpy at each and every state, and yes, we can find the enthalpy at T9 as well using the temperature T4, sorry, T2. As it was actually perfect regeneration, perfect regeneration, perfect intercooling, and reheating at the same temperature. Now, using the compression, finding the work done of the compressor. So work done of the compressor would be from state 1 to 2, and from 3 to 4. We have already got the enthalpy at 1, 2, 3, and 4. So yes, as it was the same one, so multiply by 2, that would be, so single stage multiply by 2, that you can find the work done of the compressor, which is 208.24 kilojoule per kg. The work done of the turbine as the reheating was at the same temperature, and the compression ratio was same. The turbine, again, the work done of turbine at 6 minus first stage multiplied by 2, that would be 685. The net work would be equal to 477.04. Now, the question was actually whether if we are using the regenerator, although we are using the intercooling and reheating, but let's find the thermal efficiency without regenerator and thermal efficiency with regenerator. So if we are not using a regenerator, our heat transfer would be from 4 to 6. And if we are using the regenerator, our heat transfer would be equal to from 5 to 6, somewhere here. So let's find the regenerator. And yes, the heat transfer is from first heat transfer without regenerator will be from 4 to 6. And also we have got a reheating from 7 to 8 as well. So we will be using the primary combustion chamber, and obviously the reheating combustion chamber. So the primary combustion chamber is actually from the enthalpy is actually 6 minus H4, as it was from 4 to 6 combustion chamber, and reheating was from 7 to 8. So the heat in is actually 1334.30, and our work done is over here. So the back work ratio, which is the compressor work divided by the turbine work, is the compressor work is 208.24, the turbine work is this one, so the back work is 30.4%. The thermal efficiency without regenerator, it is equal to 35.8%. If you have got an access to the Yunus engine book, there, just look at the example 9.5, which has got the single stage compression and single stage expansion. Over there, they say like the the backwork ratio improved by 40%, from over here it was actually 30.4. So the backwork ratio is improved at 40.3 was previously, and now it is improved to 30.4. But the thermal efficiency dropped from 42% to 35%, 35.8%. Now let's move towards the regeneration, and we are assuming like it will be a perfect regeneration. So for perfect regeneration, we are having the enthalpy, which will be actually, we are adding the heat in a regenerator from 4 to 5. So we will be decreasing this, or we will be subtracting this heat, and all this is from 9 to 10. And obviously there is a heat loss from 10 to 1. So the for a perfect regeneration, the heat would be transferred in a combustion chamber from 5 to 6. So using that one, so perfect regeneration is actually the heat transfer from 5 to 6, and obviously from 7 to 8 in a reheater. So that would come up as the heat in would come up as 685.28, and previously it was the heat in was equal to 1334.30. So now using this one, the thermal efficiency would massively improve to 69.6%. So this is actually an example of the perfect regeneration, or the regeneration using a single stage intercooling and single stage reheating. Now the question is like whether increasing the stages of the compression and increasing the stages of the turbine would improve the thermal efficiency or not. So if I'm using the thermal efficiency of the Ericsson cycle or thermal efficiency of the Carnot cycle, that would be equal to 1 minus TL by TH, the low temperature and the high temperature. So the low temperature is 1300 Kelvin, the high temperature is 1300 Kelvin. So using the Carnot efficiency, which is the maximum efficiency possible for the heat engine between two reservoirs or two temperature zone, the efficiency come up as 76.9%. So comparing this with the previous, which is 69.6%. Now, even if I'm using the very multiple or the too much stages of the intercooling and too much stages of the reheating, my the efficiency only and only improved by 7.3%. While in a previous case, it was actually improved by single stage, it was improved by 27%. So this is what actually the matter of the economy as well. So this 7.3% at this point cannot be economically justified. Like we cannot actually put more intercooling and put more reheating in order to improve the efficiency. So in most cases, you would be finding like single intercooling or in or like double intercooling, and yes, single heating or double reheating. But in mostly cases, like there is no need of increasing the intercooling and increasing the regeneration. Sorry, increasing the reheating in a turbine. I hope like you understand this question, and I hope like you understand the Brayton cycle with regeneration and intercooling and reheating. If you have got any question, you can actually write it down in a Google Classroom, or you can actually write the in a comment section on YouTube. Thank you very much. Have a nice time.